Hello, this is Ty Newell, and I'm coming to you today from Duluth, Minnesota, where I'm attending the Duluth Energy Design Conference. And if you haven't been to Duluth, it's just a spectacular setting on Lake Superior. But also this conference and similar ones like the Efficiency Vermont Conference and the Energy Design Center, Better Buildings Conference. Lots of excitement in the building community. Lots of homeowners, builders, architects, really looking for how to put together a home today that meets homeowner expectations in a healthy home, a comfortable home, and a durable home. And we're glad to see that theme continuing with our attendance here. So today, our topic is smart ventilation and smart air distribution, and to give you our idea of what this means, how we interpret it, what we're doing about it, and then where we plan to go in the future. And let's see if I can. There we go. Sorry for that delay. I'm just making sure I see how to advance slides. And so we'll talk about what we call smart ventilation, and then kind of the unspoken, undiscussed area of smart air distribution. Every bit as essential as ventilation, but unfortunately something that keeps getting swept under the rug from our viewpoint as we participate in many, many projects around North America. I'm Ty, and Ben Newell and Alex Long, the three of us are Build Equinox. We're all mechanical engineers, and we come from the middle of nowhere. And as I regularly tell people, I enjoy being from nowhere. We're in central Illinois, Champaign-Urbana, Illinois, and that's where we manufacture what we call the SERV-2 smart ventilation unit. And you can learn more about that on our website. That's not the direct purpose of today's talk. Our mission overall is working toward helping to live a sustainable lifestyle, one that's healthy, comfortable, and provides a future for the upcoming generations. And I'm not too far away from the land of Aldo Leopold, central Wisconsin, where I think he said it better than anyone: how do we live on a piece of land without spoiling it? And we're proud to say that we are a 100% solar powered business. And if you look over our archive newsletters, you'll see how we did that in a 4,500 square foot Morton building. And we're pleased to say that that technology is alive and well in the US, and that things are getting manufactured, as evidenced by our SERV unit. So today we're going to talk about smart ventilation and smart air distribution. And as with our other webinars, behind this webinar are some reports that you can download from our website with a number of references and links to other information. And so if some of these terms aren't so familiar to you, there's a lot of detail included in those reports that you can download from the publication section of our website. And so I hope that this pace, it's really meant to hopefully identify some areas that maybe you're not so familiar with, and to pique your interest so that you do look into these topics more. So smart ventilation, we'll upfront talk about our conception of it, and then we'll go through and identify why it not only results in better air quality within a home, but why it is also more energy efficient. And then smart air distribution. And the two facets of smart air distribution that we'll discuss are recirculation, something that unfortunately for many homes, they're being built without the ability to recirculate air within the home. And this is essential for good air quality, and we'll discuss those reasons as well as see the effectiveness of recirculation as far as maintaining good air quality in a home. And then when recirculation is not sufficient, as we get to larger homes or more complex homes, how zone control can let us more precisely deliver good quality air where the home is occupied. And we'd like folks to remember that these decisions, if you're embarking on constructing a new home and you're thinking about your own specific needs, that you think beyond that to the 5, 10 or more generations of folks that may live in that home, so that you design with flexibility and one that will extend beyond your own personal needs. And that's also kind of a lead in for next month's webinar, where we will talk about designing exceptional homes for exceptional people. And you'll read more about that as we get closer, but our newsletter, which just came out, has the initial flyer on that. And so we hope you'll join us for that webinar as well. So smart ventilation, just kind of a bullet point list of a few ideas. To us, a smart ventilator, it needs to understand air quality by measuring pollutants and then ventilate when those pollutants get out of hand. And currently, those pollutants that we measure are carbon dioxide from our respiration. And then if you do have gas combustion, gas cooking, the carbon dioxide that's exhausted from combustion sources like that. And then total VOCs, which currently is a very important technology for managing air quality in a home. As we'll see in data, VOCs typically dominate the air quality and are the main reason for ventilating, but also to recognize that both are needed. Sometimes CO2, sometimes VOCs will dominate, and we need to be able to trigger fresh air on either of those. We also, with a smart ventilator, need to sense when it's nicer outside than inside and to maximize free cooling. Some places that may not be very long, maybe 1, 2, 3 months, when there may be some nice conditions outside relative to inside. Other places like our friends in Colorado in the Intermountain West, where you might have 7 or 8 months that have wonderful fresh air at night. And then by storing fresh air, by filling your fresh air, equivalent to opening up a window, except it's automatically done and the air is filtered, that you can then delay or minimize the amount of fresh air that you might take in during the daytime when air is more polluted, it's dustier, typically, as well as not as nice from a conditioning standpoint. A smart ventilator should have high energy efficiency, that is, some manner to automatically exchange energy when it's beneficial to do so, while maintaining excellent air quality. And we feel it's very important to have the ability to collect and store data. This day and age of online data, it's very important the data is protected. It's very important that the data is your data for any system that you might start up. But we'll discuss some of the reasons why this data archiving is going to improve the wellness and health of each and every one of us, both personally as well as collectively. And then finally, even though the technology behind a smart ventilation system can be complex, It's very important that it interacts in a very unobtrusive, in an automatic, in a background manner. We don't want this technology taking over someone's life. We want it to be in the background. And as we see in many of the home projects we're involved in, really providing a peace of mind so that people can do the things that they would like to do and not have to be stressed or worried about whether or not their home is being maintained in a healthy manner. So smart air distribution, it's essential, every bit as essential as bringing in fresh air. And to us, this means that fresh air gets where it's needed, when it's needed, and that it maintains a higher quality throughout the entire house. Every space in the house needs fresh air. Bathrooms, laundry room, pantry, closets, everywhere should have air flowing through. One room that's any worse than another. And smart air distribution makes sure that all the fresh air brought in is used, which we're seeing in many, many homes. Air recirculation, which is an important part of smart distribution, is essential. It utilizes fresh air that's stored or has been blown into unoccupied zones of a house. It's also a means for filtering out indoor particulates, which in today's high performance homes, most particulates are generated indoors as opposed to being outdoor particulates that infiltrate into the home. And then finally, recirculation improves comfort. It de-stratifies a home. It helps keep the house more uniform in comfort. And comfort's important. We're more productive when we're comfortable. Finally, zone control can be layered on and added in. And we'll talk about some of the technologies that we employ in order to accomplish it. But where today's average home size is about 2,700 square feet, but the typical occupancy is 2 to 3 people in that home, that more sophistication may be required in order to open and close dampers into different regions so that we get fresh air where people are living and we minimize those areas where they're not occupied. So let's talk a little bit about exceptional homes. Here's a couple of pictures we're very proud of because we're part of these homes. The 2019 Solar Decathlon Africa Award winner, Inner House, which included Colorado School of Mines and then their partnering institutions in Morocco. They won first place last fall. And then more recently, Acorn Glade, a Tom Bassett Dilley home. He's one of the premier passive house designers in North America. This home was awarded the best single family and Source Zero project home. And you can find more about each of these homes online at any time. We're glad to be a part of those homes. And to give you an idea of some other high performance homes, and also we want you to understand that high performance, high energy efficiency, and smart ventilation are not exclusive, and that these homes are from this Illinois home, also a passive house by Tom Bassett Dilley, this Colorado home, the first passive house in Denver, this first passive house in South Carolina, first passive house in Florida, and then this Vermont home, what's called a Vermont home. Vermont is building these modular homes, very high performance. 13 homes that we monitored over a 1 to 2 year period, we found them to exceed both European passive house as well as the North American FIAS passive house standards by 20%. And in a small 1,200 square foot home with occupancies varying from 1 to 5 people in that house, these are very difficult homes to make that energy standard as well as to maintain good air quality. So we want you to know you can have your cake and eat it too as far as energy efficiency, and good air quality. The way we do it is through our Serve-2 ventilation system, and I won't go into the details. This picture is just merely meant to say from the basic unit on the left, which many homes just simply plop that in, connect it to the ducting system, versus more complex homes. And this particular unit went to a larger home, and then all the types of zone dampers, and then battery-free wireless distributed sensors that can be linked seamlessly to the CERD for managing air quality. This is just to verify smart ventilation works. No ifs, ands, buts about it. This plot is taken from 34 homes in Vermont. These are all Vermont homes. And these particular homes, relative to the set point that the home occupants use with the serve, and the predominant set point that people are using is about 1,000 parts per million of CO2 and total VOCs. If either of those exceed 1,000, they go into ventilation mode. And you can see that for the most part, with only 2 exceptions, one that has maybe a little bit higher than average VOC than the set point over a 6-month range, and then or a 5-month range, and then a second home that's right at set point. And both of these homes basically are emitting VOCs at a level that requires almost continuous ventilation. The brown dot showing CO2, this plot also gives you an indication that VOCs, the blue dots, tend to be higher than VOC, than the CO2 brown dots. Not every case. There's a couple of cases here where the brown dot, like the one that has a set point of about 950 parts per million, that CO2 is the dominant pollutant. And we'll talk about that more in a minute. But in general, most homes that we see, and these are homes with, these are affordable homes, folks who may not have as a priority the energy efficiency, the greenness of their home, as many folks interested in high performance homes. And as we get more to folks who are very conscientious about their lifestyle and what they're putting into the air of their homes, we find that CO2 will tend to dominate. And again, we'll talk about that more in a minute. In terms of ventilation, and this is no ifs, ands, buts about it. If we look at a home that uses the old rule of thumb, decades old, from the 1930s, from the very first ventilation studies were conducted at Harvard, that 20 CFM, 20 cubic feet per minute of airflow per person is roughly the level in which 20% of the population would be dissatisfied with the air quality. This air does not smell. If you walk into a room at this level of ventilation, you wouldn't say it smells, but there's about 20% of the populace that would be dissatisfied with that air. And that historically has been the rule of thumb we've used, even though it somewhat gets clouded within the tables and relations that the current ASHRAE ventilation standards are using. It's still roughly about 20 CFM per person. And as far as the pollutant level, the CO2 from our respiration rate, if you blow 20 CFM per person into a house, and the person is under what we call sedentary conditions, basic like office work activity, not as high level of an activity as cooking, not as high of a level as exercising, but a bit higher than, say, sitting and reading a book, and which is higher than sleeping. You would find that our respiration rate would cause a CO2 concentration of about 1,000 parts per million. If we doubled that ventilation rate to about 40 CFM per person, we would find that in the workplace, we would decrease sick days by about 40%, and that's equivalent to what the flu vaccine reduces the transmission of flu during the flu season. In other words, fresh air is just as effective and should be done in addition to vaccination. It minimizes the transmission of disease, and this is quantified with, you'll see the references at the end of this, but Professor Donald Milton, a medical doctor and public health faculty member at University of Maryland now, formerly of Harvard, ran a study with several thousand people to determine this. So fresh air keeps us healthy. There's no ifs, ands, buts about it. But it also improves our ability to sleep, it improves our cognition, and it improves our productivity. As far as ASHRAE 62.2 as a ventilation standard, and for those of you not so familiar with it, the ASHRAE standard, the ASHRAE Society, which has a committee that examines ventilation standards, and then this ventilation standard is typically used by states and communities and building codes officials as the basis for ventilation. It is not an indoor air quality standard. It is just to assure that there's some level of air blowing through a home that should be reasonable. But it, again, is roughly based on about 20 CFM per person, about 20% population dissatisfaction. More people will have more sick days if all of our buildings are following that standard, and we can make us healthier by doing better than that. It does not specify air distribution, although the version that just came out in 2019, and those of you who are familiar with this standard, it comes out every 3 years, and in 2010, the version that came out in 2010 has even less airflow. 2013 it was upped, and 2016 and 2019 are at the same level. It is still not sufficient airflow. It's better than nothing, but it's not sufficient. And what is incorporated now in the more recent ASHRAE 62.2 is an allowance for smart ventilation. And the way in which smart ventilation is assessed is through exposure. And we'll discuss what pollutant exposure means. Here's a table of ASHRAE 62.2 2016 ventilation. And as I mentioned, 2019, which just came out in the past few weeks, is equivalent in airflow levels. To just kind of cite a couple of the problems, if we look at the average US home, as I mentioned, 2,700 square feet, and the average US home has 2.5 occupants, looking at 112 to 127 cubic feet per minute of continuous ventilation flow that's layered on top of the air that leaks into a home, that infiltrates a home. We can see that while fresh air, as much fresh air as we can get is good, that now as you start getting above 50, 60 CFM per person, we do start seeing a significant energy performance penalty. We go to the other end of the spectrum, and something like a Vermont house, about 1,000 square foot home, 2 bedrooms, and this home, if it has 3 people in it, it's less than 20 CFM per person. But many of us know, or maybe grew up in, as I did, in a home that was a 2-bedroom home with 5 in the family, about 10 CFM per square feet. On average, within the home, it's not adequate. No matter how leaky it is not enough ventilation to keep people healthy, to keep people feeling good, to keep people from transmitting contagious diseases. Here's an exposure chart. This is an exposure chart that we've generated. And if you look at our webinar on new air quality metrics, you'll learn more detail about it. But we define exposure just similar to kilowatt hours of energy usage. If you use 1,000 watts for 1 hour in your home, that 1,000 watts or 1 kilowatt for an hour is 1 kilowatt hour of energy usage. And similarly, if you are immersed in 1,000 ppm of carbon dioxide concentration for 1 hour in a room, we call that 1 CO2 pollutant hour of exposure. And VOCs are a little bit different, but the total VOC sensor that we incorporate into our ventilation system, it is correlated to the CO2 output of a human. So even though volatile organic compounds, these reactive compounds like various hydrocarbons, various alcohols and aldehydes and acetones and things that the human is emitting from our respiration and metabolism, as well as chemicals coming out of our furnishings or in our cleansers or cosmetics or things. This soup of chemicals more typically are in the parts per billion range, but for this sensor and to give us a relative sense of how VOCs are relative to our respiration, this sensor is calibrated with chemical substances that are similar to what our body puts out, and it's calibrated to the rate that we put out CO2. So when our sensor says 1,000 ppm of VOC is in a room, it's saying that that's the VOC that you would measure with 1,000 parts per million of carbon dioxide from our respiration. And when we see VOC levels that are higher than 1,000, then we know that there's additional sources emitting VOCs into our air. Now, when that level is 1,000 ppm equivalent of VOCs, and you're in that room for an hour, then you have 1 VOC pollutant hour of exposure. And if you're in that for 24 hours, you would have 24 hours as that green line shows in this plot. And the same for CO2. If you're in a room that only has CO2 pollutant and it's at 1,000 parts per million, you would have over the course of a day 24 CO2 pollutant hours. Now we combine these in a vector manner, and the details of that aren't important for this, but you can see those in the appendice for the smart ventilation report that I mentioned in our publication section to see how we combine it. But overall, there's a combination of CO2 and VOCs that make us feel better or worse. And we would like that overall combined level of pollutant hour exposure to be less than 24. The yellow range shows us where the ASHRAE ventilation map would put us. It allows small homes with large occupancy to be, in our viewpoint, very polluted, up to say 70 or so pollutant hours per day. And then at the other range where a home is ventilated at nominally 20 CFM per person, this is that green boundary. And we would like people to be better than this, somewhere within the green range. These are leaky homes. These are homes built over 10, 20, 30, 40 years without any special sealing, without any special super insulation. These are just regular homes that we monitored spread across the US with about 2 to 3 weeks of monitoring. And these are daily average CO2 and VOC pollutant hours plotted on this map. And you can see that all of these homes had polluted times and unpolluted times. And we'll talk a little bit about why even leaky homes have poor air quality. Now here's some smart ventilated homes. These are 10 smart ventilated homes spread across the country, but this is a month's worth of data, and the data is daily data. And these are all electric homes. And what we see is that these homes, when it becomes all electric, are dominated by VOCs, but the VOC exposure is quite a bit less than in the previous slide for leaky conventional homes. And the shift for all electric homes toward VOCs is that the other homes that we just looked at are commonly have gas, natural gas. And when you have natural gas, CO2 will often dominate the indoor air quality and indoor pollutants. Now, this January data is also a time when homes are sealed and they tend to be more polluted. And it's just crazy to us that a lot of ventilation systems actually shut down as you get to cold weather. You need fresh air just as much in the winter as you do in the summer, and you should never ever sacrifice your health for extreme outdoor conditions. Now, also it happens that there's a January 1st was on a weekend and January 7th, and these fell within vacation time periods. And these few data points which exceed what our recommended pollutant level would be, these tended to be times when looking at the more detailed data that was collected on these homes, that it's quite obvious he's lined up with a party at a New Year's Eve party, family coming in to stay, so much higher occupancy loading and pollutant loading. A couple words as far as how you can also benefit from enhanced ventilation. If you're looking to get a LEED certification, you can get extra points by having improved ventilation. When we look at FIAS, the US Passive House International Standard, you'll find that this actually mirrors ASHRAE 62.2 ventilation quite closely. And in that same sense, it typically is not enough ventilation. And the Passive House standard out of Europe is even less so, where their emphasis is on energy, even though they do state that they want a healthy home. It just isn't the case in our experience in monitoring homes that their ventilation levels are too low and their distribution of fresh air within the home is not adequate. And just briefly on health costs to get things kind of in perspective, if all 125 million residences in the US were high performance homes, these residences would require energy costs of about $160 billion per year and roughly $80 billion for climate, that is for heating and cooling, and about $80 billion for people-related energy uses, hot water, TVs, cooking, things like this. The reality with today's housing stock is that we're maybe 4 times this level, but this will be roughly about what our homes will cost to keep comfortable and to allow us to do the things we'd like to do in our homes. The annual current costs of seasonal influenza and colds, from sick days and medications and doctor visits, is about $130 billion per year. And as I mentioned, fresh air from Professor Milton's studies show a decrease of about 40% of sick days by doubling today's minimum ventilation standard. And so we can see a very significant cut in this cost where there's not much room to make a cut in energy costs. Health is much, much more valuable than energy, and our performance and well-being is much, much more valuable. Asthma afflicts about 8 to 10% of the US population with a cost of about $50 to $60 billion per year. It impacts about 25% of households. All of us are either impacted by it directly or we know someone impacted by it. And if we could get asthma back to less than 4% of the populace, maybe down to 2% of the populace, by figuring out, but definitely by improved air quality as far as reducing asthma triggers as well as potential causes of asthma, there's another big chunk of savings. And then the big dog, the decrease in human productivity due to poor sleep due to poor cognition in poor indoor air quality homes and buildings, that just losing 10% of our productivity, which is an amount estimated by the Harvard School of Public Health, and again, that reference is cited. Here we're going over $1 trillion. And if we're off by a factor of 10, we're still talking about a tremendous amount of money. This upper graph shows the type of ventilation we're seeing in many homes today, high performance homes, in which ASHRAE ventilation is brought in. It's balanced ventilation, but when you take 50, 60 CFM of airflow and you divide it among 5 or 6 rooms in a house, and one room is getting maybe 10, 15 CFM of airflow, and the 2 occupants in that home are in this room or that room quickly gets polluted and is not good air quality. This is a 3-week plot where we were collecting data from a passive home with that type of ventilation. You can see that when the couple left the home for a period of about a week and a half of the 3-week period, the home was over-ventilated, and there was a few spikes when somebody was coming in to check on the plants and the house. And then when the couple returned home, it again returned to where it was polluted. The bottom shows a similar 3-week period with 2 people in our Equinox house. And the green bars show when it was actively polluting because the 850 parts per million threshold that we set on our ventilation unit kicked in. And so basically, ventilating when you need to, and then not ventilating when you don't, it saves energy, but it also maintains a higher level of air quality. So let's look at some specific comparisons so you can see what's going on with energy as well as air quality. In this comparison, we'll take a high performance, a 90% efficient heat recovery ventilator, HRV, and compare it to smart ventilation. And we're going to first compare based on some simulations that we've performed, but we're also going to look at field data. And this ASHRAE 62.2, we're going to use it as a basis for the ventilation schedule for the HRV. The smart ventilator is going to be based on SERV2 performance, and the SERV2 incorporates a heat pump into it rather than a heat exchanger core. And you can read about those in some of our other webinars and information on our website. In order to properly simulate smart ventilation, you can't use hourly, you cannot use monthly, which is typically the basis for like REM rate, PHPP, and other type of simulation models. When a person walks into a bedroom, walks into a living room, that room starts to change in air quality immediately. And in order to see that change of air quality, you need to be able to do 5-minute simulation, computational simulation periods in order to predict the change of air quality, but also in order to then put in the logic in the simulation program to see how to best manage that air quality. 3 homes that we'll discuss, but there's a 4th in the report on our website. 2 are the standard average average size home, 2,700 square feet with 2.5 occupants, average occupancy. 1 is at what is now for many states the typical building code level of 3 air changes per hour at 50 Pascal blower door. And then the other home is a passive house, highly sealed level of 0.6 air changes per hour at 50 Pascals. And then the last home we'll look at is a 1,000 square foot home similar to a Vermont home. And Vermont homes are sealed to generally less than 1 ACH 50, but with 4 occupants. And we'll look at how that does under the scheduled ventilation with an HRV versus smart ventilation. Here's the weather data we're using, real weather data from Urbana, Illinois. And this is an average. The temperature for this month, as much as it's oscillating over the course of that month in 2010, The average temperature is about 20 degrees, and our average long-term temperature for January is about 21 Fahrenheit. And then the wind speed is all over the place. Wind speed impacts the amount of air coming in through infiltration cracks. No matter how well sealed a home is, as the wind speed goes up, the infiltration goes up. And when the infiltration goes up to a high enough level, the need for bringing in additional fresh air decreases. It's very complex. It changes on a dime. And before we compare our HRV and smart ventilated home, let's use more of a conventional home, but a leaky home as a reference. Here's a home that's very leaky, 10 ACH 50, 2,700 square feet, 5 occupants, 4 bedrooms, the typical ASHRAE assumed loading of the house. And if we are interested in seeing if the house is keeping air quality below about 850 ppm, we would see that there's about 5, 6, 7 days when the wind wasn't blowing very much, the gray line on this, and so the pollutant levels in the home went up high. On average, when the wind is blowing, this house does have reasonable air quality, although where the leaks occur and where you live are two different things. And oftentimes a bedroom is not a leaky room. The mechanical room, the laundry room with a dryer vent, the kitchen with a kitchen vent are major sources of infiltration and leakage. And if you're not in the path of the leak from that one hole to that other hole, you're not going to benefit from that fresh air. Now, the energy usage related to infiltration in this home is about 2,200 kilowatt hours, or about $250 of the utility bill would be for conditioning the air that's brought into this house. So this doesn't assume any of the other electrical loads in the house or other heating loads due to heat conducting through the walls, windows, and roof, but purely for the amount of air that's been brought into the house by uncontrolled ventilation. Now, when we seal the house up to about 3 ACH and we run at ASHRAE 62.2 ventilation, we see that we drop that 2,200 kilowatt hours down to about 900 kilowatt hours. And with a good high 90% HRV efficiency level, we see that this ventilation level with 2.5 people, it's keeping the air quality on average reasonable. But again, I want to stress that you go into the bedroom, most likely the leaks are not there, and most likely the local pollutant levels are quite high. We go to a smart ventilated home that will trigger fresh air whenever the air quality on average gets above 1,000 ppm. We see that we drop the energy usage related to ventilation air and infiltration air by 30% from the ASHRAE ventilated home with a high efficiency HRV. So we're maintaining air quality at the desired level, and we're doing that more efficiently in the home, roughly about a $25, $30 utility bill difference. If we look at a more highly sealed home, a passive house level sealed home, 0.6 ACH instead of 3, we see that we cut the energy usage in half for the leakier home, and 3 is not a leaky home by any means. It's at the forefront of building codes in many places. But by going from 3 ACH down to 0.6 ACH with ASHRAE ventilation and a 90% HRV, we drop from about 900 kilowatt hours to about 430 kilowatt hours for the energy that's used to condition the ventilation air and the infiltration air. We look at the smart ventilated home, and now by sealing it up, you can see that we're pretty much staying, there's a lot more detail. This is over the course of January. If you looked on a 5-minute basis, you would see the smart ventilation unit triggering, dropping air quality, or dropping pollutant levels down to the lower threshold, the lower red line, and then moving back up to the higher threshold, but actively and automatically maintaining air quality at whatever threshold is set. And we again see about a 40% drop from the equivalent home with an ASHRAE ventilation standard and a high performance HRV. The dollar amount, the energy difference is now about $20. So even though that percentage energy use is less, the energy amount is not that large. The more important aspect is that this is a healthy home that's managing air quality throughout the whole house. Finally, home D. 4 people in a 2-bedroom home, something we see all the time in Vermont homes, that this home doesn't need much as far as electrical energy because it's so well sealed, and then running at ASHRAE ventilation standard, it's only running about 52 CFM into the house. But as a whole, this house is polluted. This house has poor air quality. People are going to get sick more frequently. 25% of the populace would be dissatisfied with the air quality in this home. And so even though it's only about $25 worth of the electric bill is going toward the ventilation and infiltration related energy, it's not a situation you'd want to live in. By smart ventilating this home, dropping it down to 1,000 parts per million and actively maintaining it there, we go up in energy. We go up by about 120 kilowatt hours, but this is a healthier environment to live in. And the cost of that's about 12 cents per person per day to have them live in a higher quality, healthier home environment. And we're going to go on to smart air distribution and just see what happens in a home when it does not distribute the air properly around, and then what smart air distribution, recirculation, along with zoning can accomplish. This is data from a real home. 3 monitors that we placed in the bedroom for 2 small children and a family room in the living room. This family of 5 mostly lives in the family room, and the family room and living room have fairly open connections, a double door separating the 2. But this home's somewhat unique. It was built in the 1950s with radiant ceiling heating, which means in the winter, there's no active movement of air other than what occurs naturally and by people walking through it. What you see in this is that the home itself, 1950s era home, and the blower door infiltration levels roughly about 5 to 6 ACH. So actually a pretty well sealed home because it doesn't have flue vents and other types of leaks you would find in a central furnace type home. When the young children go to bed, that air quality in their bedroom just goes zipping right up. Around 9 o'clock or so, the parents would open the door and then it levels off and doesn't tend to increase much more. But with a door closed on this bedroom, and these are old aluminum frame windows, leaky windows, there's just not enough leakage in this bedroom, as is true in many bedrooms, to keep the air quality at a good level. And this is why when you have one and done ventilation, or you do not have recirculation or zone controlled ventilation, you may distribute the ASHRAE standard level of ventilation to all these rooms in a home. But what's distributed to each individual room, if the occupants of that room are in it, that room is polluted. And it takes minutes, not hours or days, for that level of pollutant to get unacceptable. The area, the unoccupied areas in this home may not ever see a human. You may waste 80% of that ventilation air that it's not benefiting the occupants of the home. And it's instead finding its way to the exhaust register and leaving the home. And this, by not recirculating within the home, and for those who think that recirculation is bad, it's exactly the opposite. This is how you filter particulates out of a home And as I mentioned earlier, the bulk of the particulates, 80 to 90% of the particulates in a highly sealed home are indoor generated by us. Our skin flaking, our abrasion of textiles and clothing and shoes on surfaces, cooking particulates, and other things we spray into the air. So we're wasting air by not recirculating it. We're wasting fresh air. We're not filtering particulates out, which is also impairing and impacting our health. So here's a home with constant flow ventilation. This is a simulation now, and the kind of orange-brown plot shows the average air quality in the home. And on average, this home is staying roughly below 1,000 parts per million. Now, what's different about this simulation from the simulations I showed before is that this has a human occupancy schedule in it where the people are sleeping from 10 to 6 in the morning, 10 at night to 6 in the morning. They're then up for a couple hours where they're in the home, and then they're outside the home from 8 o'clock in the morning to 4 in the afternoon. Then they come home and they're mostly in the main room, in the family room. And the ASHRAE scheduled ventilation has been divided up, the 120 CFM into 60 CFM into the main room, 20 CFM into the master bedroom where 2 of the home occupants are assumed to sleep, and then 10 CFM, the remaining amount, in the other 3 bedrooms. And what you see is that the bedrooms are polluted when people are in the bedrooms at night, that the main room is overloaded with pollutants when everybody is in the main room in the morning, breakfast time, and then in the evening time. And then the red line shows if someone's sick and they're staying in their bedroom and they're receiving 10 CFM of airflow, that room is staying at about 2,000 parts per million of CO2 and associated VOCs. And this is not good for the person trying to get better, but it's especially not good for you if you wander in the room. This plot, which shows the probability of infection, and this is for rhinovirus, the flu virus, and the coronavirus, which you're hearing about so much these days, these are transmitted much more efficiently, requiring that much less time and exposure to that virus. This shows that relative to the CO2 concentration, we can predict the probability that you're going to catch the flu or a cold from somebody that's infected in that room. And so if we're at 1,000 parts per million, where that red line is, if you're in that room for about 4 hours, you've got maybe about a 20% probability of getting that cold, and 30% if you're in that room with that person for an 8-hour exposure. You go up to 2,000 parts per million. Now it's going to be about a 30 to 40% chance if you're in that space for about 4 hours, and about 60% chance at 8 hours. As I mentioned, flu is a much more efficiently transmitted disease, and CO2 is really a marker, a tracer that's telling us what fraction of the air you're breathing in that room came from someone else's lungs, which are then shedding viruses that you're more likely to collect. When you recirculate, in effect, recirculation, all it is removing the partition that we place in our rooms that keep the room from more naturally stirring and staying mixed. So what we would like to see is that somewhere less than 2 hours, that the recirculation of air is sufficient to fully turn over the house volume air. And so, for example, a 2,000 square foot home with about 8-foot high ceilings with 200 CFM of recirculation capability, what our smart ventilation system operates at, that you're going to turn over this air within about an 80-minute period. This is real data from Equinox House, our test bed, but also my home, which is a 2,100 square foot ranch. It operates with about 150 CFM of recirculation capability. This has a first generation serve unit in it rather than the second generation that has higher airflow capability. But 3 3 pollutant monitors were placed within the main room, the master bedroom, and then an unoccupied middle bedroom. And the yellow is the CERV's return CO2, what the CERV is measuring. And we have our set point at 850 parts per million. So when that yellow line would hit 850 parts per million, the CERV goes into fresh air mode. And so you can see in that first peak, when the CERV hit that threshold, it rapidly brought the return air down in pollutant level. Once it hit 100 parts per million below the 850, it switched back into recirculation mode. It was mixing air throughout the house, unifying it. And so you continue to see what's returning to the CERV dropping. But the other thing you see is that even though there are some wide variations from an occupied and an unoccupied main room, and then an occupied bedroom and an unoccupied bedroom, with recirculation, we're keeping the air quality out under control. It is nothing like the house that I showed with the one and done ventilation earlier, and it's nothing like the 1950s era regular home, leaky home without recirculation. This home doesn't exceed 1,000 ppm during this window of operation. And you can see the effectiveness of ventilating it and then recirculating to keep to make use of the fresh air that's in the unoccupied regions of the home. Now, when it takes more than 1 to 2 hours to recirculate a volume of home, for example, a 4,000 square foot home with about 200 CFM, this will require a bit more than 2 hours to recirculate it. Then zone dampering in order to send fresh air to where pollutants are being generated makes sense. And the way one can trigger and operate zone dampering, bringing more fresh air in where it's occupied and less where it's unoccupied, is through a variety of sensors. We have an array of wireless battery-free sensors for CO2 level, or occupant sensor, or switch sensor, like a light switch, but one that chirps a message to the CERV unit to tell it, I'm here, I'd like 15, 30 minutes or whatever of fresh air ventilation into this room. Or a circuit sensor, a sensor that is placed in line with a light switch and detects that there's current flowing. And so it says someone's in this room, let's go into ventilation mode. These can all be used separately, independently, or they can all be used in parallel. And to give you an idea, here's just a brief look at these sensors. We use a protocol called N-Ocean, E-N-Ocean. That is a very low powered but very robust wireless signal for letting us locally interact with these distributed devices and zone dampers in the main CERV unit. The CERV unit is the base unit, and Ocean is built native into our controls. And it's like Bluetooth that you're more familiar with, except this is more for operating a house as opposed to interacting with other like entertainment devices. And so a home that would have more complexity with multiple zones, and the number of supply zones do not need to equal the number of exhaust zones. But for example, if you had a 5-zone house and we're delivering about 200 CFM per zone to this house, these dampers can be characterized with a C value, and I won't go into detail on that, but when the C value is high when a damper is fully open, it's low when a damper is closed. And in the case of these dampers, when they're 45-degree closed, that is about 20% of the full open flow value. And the C value lets us design properly zoned systems. So in this case, if we fully open this one zone with a maximum C value and close the other zones 45 degrees, we still want air flowing through the rest of the house, but not as much. we can shift from having about 40 CFM to each zone to having 120 CFM to this one zone, and then 20 CFM to the unoccupied zones. And just another brief example, local exhaust, another way in which we can use zoning. If the circuit sensor is placed in line with, say, an exhaust hood, and somebody switches the exhaust hood on, indicating that they're cooking and they would like to have more fresh air delivered into that space, that sensor, wireless sensor, chirps a message to the serve, which then either through wired or wireless connections tells a zone damper in the return zone from bathrooms to close, not close if a bathroom's occupied, but if they're unoccupied, to close, which increases the amount of ventilation air, exhaust air coming out of the kitchen. And so it lets you meet your local exhaust ventilation goals as specified in ASHRAE 62.2. So we're near the end, and I know this is a fast-paced and hitting you like with a fire hose with information. And so both if you want more detail as well as you're having trouble sleeping, download the 2 reports on smart ventilation and smart air distribution from our publications location on our site, and the background and detail of that are there. And then this webinar will be posted if you would like to go back through it and understand more. But I want to end with, we don't view ourselves as a ventilation company. We view ourselves as contributors to our health and well-being in our homes, that this automated fresh air ventilation is crucial for improving collectively and individually our health. And we've developed a concept we call pre-ventilation. We want to use the ventilation system in concert with other things going on around us in a seamless and unobtrusive way. And this is where our online data can benefit each of us personally as well as collectively, that the serve as it operates and as it logs your data, that this data, at least as far as our system, it is private data, it is your data. You can tell us to get rid of it. It's not used for advertising or selling. It is purely used by us to continue to help improve the operation of the serve unit. And then it's downloadable by you. You don't have to sign up for anything. You can just download your data, look at it, and then within your own sense of what's going on, try to see when this data is telling you things that make you feel better and when it may be indicating things when you're not feeling so well. But we very, very strongly feel that fresh air in concert with other things that you're being immersed and exposed to, from the amount of hours of sunlight you've had, the pollen count, air pollution reports, how much you've exercised, the foods you've eaten, the people you've interacted with, how much screen time you've had on TV, how much time you've been under stress, and how well you've been sleeping. That this day and age of big data and artificial intelligence, which is just simply helping us to correlate data that is difficult for the human to see through. So how eating this food coupled with exercise or lack of exercise, coupled with the air quality that's been maintained in your home, perhaps these things will help mitigate or help you avoid about a depression, a migraine headache, maybe avoid or mitigate the chances of an asthma attack, a sinus attack. But we know for sure there's reasons why we sometimes feel well and sometimes we don't. It's not just random. And it's our intent to keep working on how to make each of us feel better. And my data, which is online and you can see directly from our site, and your data can help each and every one of us. And so that's the way we view this. In summary, the cost of poor data the cost of poor air quality and poor data perhaps is much greater than the cost of energy in efficient homes and buildings. It's time we think beyond energy. Energy is not the object, as Bill Bonfleth, former president of ASHRAE, has stated. We don't build buildings to save energy. We build buildings to keep people healthy, comfortable, and secure. And energy is a constraint. We want to do this in an energy efficient manner, in a sustainable manner. Smart ventilation is a way to take that next step in automating and managing air quality so that you can be relieved of that. You can be relieved of the stress. You can have the peace of mind that you can enter your home and it is your safe haven. You can breathe easily and it's going to keep you healthy. And smart ventilation, as we've seen in many of these cases, it's more energy efficient. It delivers fresh air when you need it, and it makes sure that it's delivered where you need it. Smart air distribution, recirculation is essential. Step number one, air needs to be recirculated in the home. Get particulates out, make use of fresh air stored in the unoccupied areas of your home. And then when recirculation alone isn't sufficient, when you don't turn the volume of a home over within every 2 hours, that then zone control, layering on that next level of seamless automated control, perhaps with diffuse distributed sensors to aid in the detection of that. And any questions about that, contact us anytime. We can help you figure out how to get the type of system that you need for the home that you're designing or that you're living in. I want to thank you for taking the time of being with us today. For sure, contact us anytime with questions. I'm sorry I breezed through this and for the questions that may have been asked that I had difficulty walking and chewing gum at the same time. So it's hard for me to follow the questions in that, but possibly Ben has been monitoring the questions and then and so any of those questions that I may not have answered, for sure feel free to get back with us. I mentioned these references, which you'll see in those reports, but there's hundreds and hundreds of references. These are not cherry picked. These are substantial references from folks involved in research, in peer-reviewed literature, and these will lead you on to other things. But the Harvard studies on air quality and cognition productivity, Donald Milton studies on transmission of viruses and disease, along with fresh air ventilation and reduction of illness, as well as Lawrence Berkeley Laboratories, which is one of the leading institutions in the Danish Technical University, really where air quality studies and the importance of air quality in the modern era has begun and continues to today, that these will provide you additional background in these. Well, thank you very much for joining, and we hope you'll join us next time. Bye-bye.